All right, well, hi everyone. I'm here today to kind of talk representing Dennis Bondar's group, although I'm not the only one. There's a talk later by Alex Schimler that you'll see. But what I'm going to try and talk about today is a use for a method in quantum control called tracking control for being able to discriminate between different species of material in a mixture. And I'll try and kind of highlight some of the connections to quantum information that happen along the way, provided my computer does not go to sleep.
It might be the pointer. Oh, okay.
Yeah, I think that's okay. So, yes. So I'm an environmentalist, which means I recycle everything, including jokes. So some of you may have seen this before. But to start with, the question is, what do quantum systems have in common with James Bond? And the answer to that, obviously, is that if you want them to do what you want, you have to fire a giant laser at them. So, yes, that's the motivation here. So, what I'm going to talk about is quantum control. And to give some context about this, you can think about quantum control in three broad categories. In all cases, because in a quantum system, the way we can kind of, the experimental evidence we get out is always in expectations. Control is about trying to control expectations rather than necessarily the quantum state itself. And you can divide these into three broad categories. So if a laser works here, maybe not. The first one is what you call local control. And the only idea with this is that you have some expectation, and all you really want to happen is to have a monotonic increase in this. So a really simple example of something where you're instituting local control is, let's say you have a free particle, and you wanted to increase the momentum as time goes on. Well, you just apply a constant field and the momentum will go up. And that would be a very crude form of local control. So this is in some sense the easiest version of control to institute because you don't actually care what the value of the expectation is, you just want it to be going up. Separate from this is what I'm going to be talking about today, which is tracking control. And in this one, you specify a trajectory that you want your expectation to follow. So in some sense, you can almost think of it as a kind of time-dependent version of local control, whereas with local control, you just want something to go up and you don't really care about the time dynamics. With tracking control, you're trying to put the expectation at a precise point at each point in the at a precise value in each point in the evolution. And on the left here, this is from a collaborator who I did the work I'm going to be showing you today with. This was something else they did with tracking control, where you have kind of a molecular system in 2 dimensions and this kind of phi angle that's an observable, and by controlling your electric fields in the x and y component, you can kind of make it do more or less whatever you want, up to and including writing things. Finally, just to kind of make a little bit more of a connection to quantum information and computing, thank you very much. We have optimal control. And with this version, what you're trying to do is, starting from a given quantum state, you want to find the most efficient way to get to a final state such that you're maximizing some kind of expectation at the final time. And this is always based on a kind of variational principle. So you go through every possible path from the initial state to the final state, and you want to get the best one subject to some constraints. And this is related to certainly quantum computing, because when you think about an algorithm in actually implementing this, essentially what it is it's going to be a unitary kind of transforming some initial state into a final state. So optimal control is very closely related to actually implementing quantum algorithms. Okay, so why is quantum control useful? Well, specifically in the concept of tracking control, if you can control expectations, especially if they're order parameters, that gives you, in a sense, an indirect control on the phases of matter in a system. And so if you're able to do this, you can kind of think about dynamically driven phases of matter, so things like optically induced superconductivity. Just to give you a final kind of thing on tracking control, the specifics here aren't too important, but I just want to give you an overview of how tracking control would work. So you would start with some target expectation, so in this instance it's the current. And within your system you have some control field, say phi, and it's coupled to some other Hamiltonian. The idea is that what you want to do is you want to find an expression for your control field in terms of the expectation that you're trying to track. Because at that point you can just kind of put in the trajectory you want for this, this gives you an answer for what your control field should be, and when you then substitute this into your Hamiltonian, you can then use it to propagate the system wave function. The trick with this is that this depends on other expectations of the system state. So what you end up with when you kind of look at this, you need to calculate some system expectation. This would go into your expression for your control field as well as your expectation. And so effectively the evolution equation you have for all of this is non-linear in the sense that it depends, if I were to kind of put in here explicitly, you'd see expectations of psi in here. So this is for a specific model, but the general idea is quite generic for tracking control. Put this in, find an expression for the control field based on the expectation, and then evolve using that. Just to give you some examples of some of the things you can do with tracking control, here's something from some papers we're just about to publish. They should be coming out in a couple of weeks now. But let's take a couple of examples. So this is in something called the Hubbard model, where you have two parameters, u and t naught, and it's the ratio between them that determines the phase of matter, if you like. So in the Hubbard model, you have a conductor when this ratio is 0, and then for all finite values, it's an insulator. And one of the things you can do with tracking control is if you take some reference optical output, you can use tracking control to kind of swap the response of the system. So here you can see that in the conducting state, we get something like this. And if we use an appropriate tracking field for an insulating state, we can kind of reproduce the conductor's current. You can kind of see here in the spectrum that essentially what's done is you've swapped the dipole spectra between an insulator and a conductor in this example. But of course, you also have arbitrary control over your expectation. So here we've got two examples. One which is slightly more physical, where you think, okay, I've got this kind of spectrum, but I want to boost some of the XUV emission. And so you can kind of then design a field to do that, a control field with this tracking control algorithm, or you can just think about an arbitrary shape like a switch. And one of the things you can see here is that in this case, as you move further away from this metallic state, you get more and more non-linearities between what the fields you need is to produce the current, between the control field and the current you produce, as you can see here. So that's the background. And there are a number of uses for tracking control. But one thing I wanted to talk about here is one way you can use this to maximize the efficiency of determining relative concentrations of systems in a substance. So it could be kind of a set of crystals in a solid, and you want to know kind of what's their relative concentration, or molecules in a solvent, anything like this. The specific dynamics is sort of irrelevant. But the idea is that we think about a mixture of non-interacting systems driven by an external field. So something like this. So we have this mixture with relative concentrations of these different systems, and they don't interact, but each of them has their own optical response. And so what you get out at the end is going to be some summation of all of these things with their relative concentrations. And the idea is to say, okay, given I have this output at the end, and I know what kind of potential species I have, so I know the kind of the pure system's optical responses, I have a library of these, can I determine the relative concentrations just from this? So you know your JKs, and you know your final output J, and you want to find this NK, these densities. Well, one of the simplest ways to do this is to think about it just in terms of a linear algebra problem. This is a little bit of an abuse of notation here. I've written it as a vector, but really you can imagine that you have something that for each time point you have the current at that time. So this is going to be a very rectangular matrix, really. But the overall current is going to be given by these relative concentrations, and then this library of your kind of pure optical responses. And so looking at it like this, you would say, okay, this is a really easy problem, right? That all you do is you have to find the inverse of this matrix, and that would automatically give you the concentrations. So you have your output, and then you have this matrix that you want to invert, and that should give you all of the concentrations. There is a problem with this, however. And that's mainly that you have a lot of time points and you have n species, and this becomes a kind of very rectangular matrix. And it means that the problem is kind of massively overdetermined. What this can mean is that you can get almost singular matrices here. So when you try to do a direct inversion, what you'll find is that any numerical job, like any pseudo-inverse, anything like this, won't do a very good job. So, and what this ends up leading to is quite large errors in the determination of your relative concentrations. So if you have individual systems which have very similar optical responses, you get quite large errors in kind of determining what their concentrations are. One way of characterizing how difficult this sort of matrix is to invert is by the condition number, which is the ratio between the largest singular value of the matrix and the smallest. So the bigger this gets, the harder the matrix is to invert, and while you can invert it, the bigger the errors you'll get in the concentrations you end up with, as we can see here. So where does tracking control come into this? Well, what we'd like to do is we'd like to minimize these errors. And so the way to do this is we want to kind of maximize the distinguishability between the individual optical responses in your mixture. So if we have some set of, say, 5 species of molecule in a mixture, and we want to know their relative concentrations, we can't change their intrinsic response because that's what the material is. But the thing we do have control of is the field that we're kind of driving them by and watching the response from. Now in the kind of simple example before, I just took a transform limited pulse, and you get all of these responses. And it turns out that this is with this output, it's quite hard to get the N0, N1, N2. But we have control over the pulse. And I've already been talking about tracking control, so hopefully there's a connection is kind of becoming more clear now. That if we use tracking control to design a pulse, we can kind of maximize the distinguishability between species and minimize this error in the inversion. So what is our strategy for this? What's the easiest way to kind of maximize the distinguishability? So if we start with a kind of pump pulse, just to make sure that there is an optical output, we can think about these 3. I'm taking 3 species as an example here, but it scales very well, this algorithm. So you start with a pump pulse and you see, okay, there's some response in all of them. The trick then is to use tracking control to determine, you pick some species, you say, for the next time period after the pulse, what I want to do is I want to send the optical response of this species just to 0. So this then is kind of using tracking control on what I've already seen. I take this point, and then I just evolve for some time using tracking that makes this current 0. And then once I've got that field, I can evolve all the others in the same way, up to some determined time period. So taking kind of some base frequency and saying I'm doing 1 period for each of these parts. That didn't really make sense. So once I've done this first species with tracking and found what the responses of the other ones are to the field I derived, I now change it. Now I track the second species after this. So now I'm tracking so that the second species optical response at this time goes to 0. And once I get that tracking field, I then evolve all of the others. I'm aware that with the black lines, these look like discontinuities, but they're not. There is kind of, they're just quite steep changes around these points. So then finally, you can imagine I have a third species, and then I just decide, well, now I'm setting this third species to 0. And so it doesn't matter how many kind of internal species you have, what you want to do is you want to try and build up a library of everything that you could possibly have in your mixture, and then design a single pulse so that you know at different times, different species responses will be set to 0. And it might not be totally clear why this would matter, but it turns out that when you do this, okay, you get a much different looking pulse, but then you're guaranteed that at different times your optical response is 0. And the effect of this really is that if you kind of include this explicitly in your algebra, when you're doing the inversion, this reduces the degree of overdetermination in the problem by quite a lot, which helps, again, with inverting this kind of big matrix to find these relative concentrations. So, as I said, by designing this pulse that will sequentially switch off optical responses, you're reducing the degree of overdetermination, and this yields much smaller errors in your relative concentrations than using some naive determination method. The other thing about this method is that you're only doing it once to design a pulse that will turn off each of your species. So the cost of actually calculating this doesn't really depend on the number of species present in the mixture. You just kind of divide up however long your pulse is going to be into the appropriate number. The other thing about this method is that it's quite generic. It doesn't matter kind of what the internal dynamics you're talking about are, as long as there's some link between the expectation you're trying to look at, which is the current here, and the control field, so that you can kind of describe the expectation that you want in terms of the control field. So finally, I'm going to show you two different examples of using this. So this would be a case of kind of using it in a molecular system. So here we have three species of molecule: hydrogen chloride, hydrogen bromide, hydrogen iodide. And here are kind of two different potentials you could use for these. So these kind of dotted lines are something like a Morse potential, and here this is just a dipole potential, the solid lines. So the only thing that distinguishes these three molecules actually is their relative mass. They all kind of behave, they're all under the same Hamiltonian, and these kind of potentials you see are just due to their different relative masses. And so if we kind of apply our tracking strategy to this, we've got something here that we're calling a naive approach, which is where you just use a transform limited pulse. You throw that into your mixture, so you have some random numbers determining the different concentrations, and you see what the output is, and then you just try and kind of invert that. And what you'll see is that here, this is kind of depending on pulse number, the length of your pulse, the condition number for both our tracking approach and our naive approach are more or less the same for a short enough pulse. But as you increase this, the condition number for our tracked approach goes way down. And what does that mean? Well, we can actually kind of properly characterize this in terms of the error. So if you have your vector of concentrations that you calculate, and then the actual target vector, which are the true values that you used, and you look at the kind of the norm of the difference, this gives us our error. You can see here that this kind of naive transform limited pulse, the errors are kind of 10 orders of magnitude higher than what you get with tracking. So this kind of in this molecular case seems to be quite successful. The other part, which is kind of more where where my interests kind of lie more, is in these kind of solid state systems. So here you can imagine a kind of inhomogeneous crystal with impurities that kind of aren't interacting. So rather than this molecular model, we have something like a Hubbard model here, where you have hopping and on-site repulsion. And so, yeah, this graph got produced in a hurry. In the previous case, it was kind of changing the length of your pulse. Here, what we're thinking about is just a two-species discrimination, but the way we're kind of distinguishing the two species is the size of this on-site interaction. So what this is saying is that what's the difference in U between these two materials? Because this is the only thing that will distinguish them. So going from kind of, there's a difference of 0.1 down to kind of 1 in a million difference. So this is really for very, very similar materials with very similar optical responses. And what we see is that if we use our kind of naive approach of a transform limited pulse on just these two species, as we make the systems more and more similar, the condition number goes way up. And when we actually look at the error, calculating the same way as before, at kind of relatively large differences, this error is still kind of on the level of numerical precision. But then as you make the systems more and more similar, this error goes way up for the naive approach. Whereas this tracking approach stays more or less on the level of numerical precision. So I think that is more or less all I wanted to talk about here. One more point about this, just to try and kind of bring it back a little bit to quantum computing and information. You might ask, okay, what is the point of being able to determine different concentrations in a mixture? Well, first of all, I think that's something that's kind of generally useful in engineering. It's something that's already, you have to use things like maybe mass spec to do this. This is a non-destructive method. But also, there's a lot of interest at the moment in things like molecular computing, where you can use chemical reactions to perform a computation. And then you have to be able to read off the relative concentrations of these things. So this is a kind of potential method of doing this non-invasively. So, to summarise, since this is a talk about control, I thought I'd show you someone who has none of it. So what we've done here is we've used this tracking control method in quantum mechanics to and applied it to a specific problem of determining the relative concentrations of a mixture. So there are other uses, this is just one. And what we found is that this is still a work in progress, but if we use a designed pulse to discriminate between species, the errors that we get are orders of magnitude smaller than just using a simple kind of dumb pulse. So obviously there will be open questions about this, about how experimentally feasible is it to generate the laser pulses that you've seen. If you ask me a question about that, I might be able to answer. But at the moment it looks kind of promising. But again, work in progress that's being done with, as well as Dennis, Alicia McGann and Herschel Ravitz in Princeton. So yeah, I think that is me done, actually.